Okay, so we've looked at Compton, who looked at X-rays being emitted onto a piece of metal and then ejecting the electron. De Broglie said that if we could do that with the photoelectric effect, where we just submitted UV light and visible light towards a plate, or Compton looked at X-rays, de Broglie says if light, and then really all of EMR, could have particle properties, then could electrons and protons not have wave properties? And this again goes towards the wave-particle duality theory, where we see both happening in energy. So what he looked at is he looked at this concept. If we have momentum of an object, we know that momentum is equal to mass times its velocity. And we investigated that lots in the first unit. But if we had momentum of a wave, we see that it is related to its wavelength. Then could we not say that mass times velocity is equal to Planck's constant over a wavelength, where wavelength would be equal to Planck's constant over mass times velocity? When we look at the wavelength of an electron, we call this a de Broglie wavelength. So when we're looking here, this is momentum of a photon. This is not a momentum of an electron. When we put these two together, then we can start considering looking at an electron. When we do our unit analysis, we see that we have Planck's constant, which is joules seconds, divided by mass, which is kilograms, multiplied by meters per second. And we see here, if we expand out a joule, it'll be kilograms meters squared per second squared. When we start canceling things out, we get the meter that cancel out here, the second that cancels out here, but also the second that cancels out here. And so we're left with just a meter. And this is the experiment that was done to prove it. The wavelength of a particle is often referred to as the de Broglie wavelength. So G.P. Thomson, not to be confused with J.J. Thomson, but G.P. Thomson demonstrated that electrons could be diffracted, similar to Young's double-slit experiment. So Young took a beam of light and he sent it to an opening, and then he caught it on a plate. And again here, at these points, we would see bright lines. And where we don't see contact, there would be a dark space. So we saw that pattern. Also, if we looked at sending in an electron beam into these crystal surfaces, we would see diffraction back towards a detector, and then we would be able to go through with that theory. Note that this distance here between these components is 3 angstroms. And I'll leave it to you to Google how small an angstrom actually is. The first example, an electron has a mass of 9.11. Again, that's given on our data sheet. Calculate the de Broglie wavelength for an electron traveling at this speed. So de Broglie wavelength is the combination of the momentum of an object and the momentum of a particle. And it's asking us to calculate the wavelength, so h over mv. When we put in our knowns, this will be in joules. We need the kilograms meters squared per second squared for unit analysis and not the electron volts. That's not the same units. So wavelength is going to be equal to 6.63 times 10 to the negative 34 divided by 9.11 times 10 to the negative 31 multiplied by 2.15 times 10 to the 6. And we should get a wavelength of our electron 3.38 times 10 to the negative 10 meters. All right. Calculate the wavelength of an electron that has kinetic energy. When we see this combination of words here, the wavelength of an electron, we're looking at de Broglie. Because an electron is not a photon. Okay? And because it's not a photon, we cannot use hc over lambda. We can't use that formula. So let's write down a list of what we know. We know the energy is 3.10 times 10 to the negative 16 joules. We're talking about an electron, so mass must be 9.11 times 10 to the negative 31 kilograms. Because we're looking at a de Broglie wavelength, we know that mass times velocity is equal to h over lambda. If we are missing pieces of information, we can just keep working. So how do I find velocity? Because it's not given to us to just assume 3.0 times 10 to the 8. Notice that we didn't do that in this question here. Well, energy is equal to 1/2 mv squared. So v is equal to 2e k divided by m all square rooted. That's how we find our velocity. And so we're going to get 2 times 3.1 times 10 to the negative 16 divided by 9.11 times 10 to the negative 31. Our velocity is going to come to 2.61 times 10 to the 7. Again, you're going to keep all of your decimals. And now I can go back and I can calculate the wavelength by entering in the information. 6.63 times 10 to the negative 34, always using the joule version for Planck's constant. 9.11 times 10 to the negative 31 multiplied by 2.61 times 10 to the 7. And our wavelength of our electron is going to be 2.79 times 10 to the negative 11 meters. All right, this is the last lesson in our EMR unit. Woohoo, big celebration. But I want you to work on these questions at the bottom of the page, 1 and 2, and then 4 through 7. They're intermediate, so you actually can do them. They're just going to be multi-step, probably looking at different ways of obtaining that information.